simple. That you see here there is the spin up and down quasi-particle spectrum. They overlap each other. But the endeavor is to actually do something like this: is to like have a Zeeman splitting of the quasi-particle spectrum of superconductors. Okay. How do you do this? Okay. So if you do this, the net spectrum will look something like this. Okay. So you are adding up the up and down spins here, like everywhere basically. Okay. So how do you do this? Obviously you need a magnetic field, but you see that we have a problem, because if you subject a superconductor to a magnetic field, the magnetic field will most generally couple with the charge. Okay? If it couples with the charge, like if it couples with the charge of electrons, it will produce these cyclotron orbits, and then you will get the critical field of the superconductors. So it's not a very simple problem. However, there is a way out, and the way out is the following: that you make the superconductor film very thin, and you apply the magnetic field in plane. So then what happens is, the electrons, like very thin means the film thickness should be lesser than the London penetration depth and the coherence length of the superconductor. In such a special case, the electrons will not have the ability to respond, like the charge, the magnetic field, like coupling with the charge will not. Okay. Yeah. So in such a case, the cyclotron orbits cannot form. And what will essentially happen is that you will get a Zeeman kind of response from the quasi-particle spectrum. Okay? And in such a case, there is this famous Chandrasekhar-Cluxton limit, which says that you can actually have superconductivity which is limited by magnetic field up to this kind of value. So typically for niobium nitrate, this is in the order of tens of Teslas. Okay? So that's very exciting. Is there any proof of it? Yes, there is proof of it. So these are very old experiments, 1970s, MIT, Francis Bitter National Magnet Laboratory. So what they have done is that like you have a tunnel junction which has aluminium oxide and silver, and like the tunneling integral, current integral, and the differential of that is essentially a image of the density of states. And when you apply magnetic field, what they saw was that these two peaks, they scale linearly with magnetic field. So that is the Zeeman response that you are looking for. Okay, so you can actually do this kind of Zeeman splitting, and maybe that can help you to do spintronics with superconductors. The most important thing, as far as my work is concerned, is this particular result from the same lab, now by Dr. Jagdish Modira in the 1990s. So what he did was, he measured the same structure, but this time he had this ferromagnetic insulator, europium sulfide, placed underneath that thin aluminum film. And what that did was, so the idea is the following: that the Cooper pairs in the superconductor, in that thin superconductor, will reflect off this ferromagnetic insulator interface. When it does so, it will experience an exchange interaction. And because the superconductor is thin, like all the Cooper pairs and all the quasi-particle spectrum will actually be correlated. They will carry a memory of this exchange interaction. And as a result, it's like the effective molecular Weiss field of that ferromagnet will extend onto the superconductor. And even without applying a magnetic field, external magnetic field, you can actually get like the degeneracy lifted in the quasi-particle spectrum. Okay, and this was shown by these like DOS measurements. So where you see that like at very low fields or even at no field, you actually have these double peaks forming over here. Okay, so with ferromagnetic insulators, you do not need an external magnetic field to generate this kind of quasi-particle spectrum. Okay, then comes one very important thing. This field, effective field, is not the lines of force of the ferromagnet that is coming out. It is actually the effective molecular Weiss field that is inside the ferromagnet that is extended onto the superconductor. Okay, this brings me to the next important idea. This was proposed by Dujons. He won the Nobel Prize for his work on polymers, but did a lot of foundational work on superconductivity before he moved on to polymers. So this is the idea of a spin valve. So he wasn't aware of these experimental results. He wrote this paper in the 1960s. So what he says is that you make a superconductor very thin, lower than the coherence length, much lower than the coherence length, and then you sandwich it between two ferromagnetic insulators. He assumed that there would be this kind of exchange field inside the superconductor, and now depending on the relative orientation between these two ferromagnetic insulators, you will have an exchange field inside the superconductor. You see, when this theta is 0, this H is finite. When this theta is 180 degrees, which means that when the ferromagnets are anti-parallel aligned to each other, then you have H essentially going to 0. So which means, like, you can actually engineer something like a sandwich like this, where in the antiparallel state you should get superconductivity because H is 0, but in the parallel state you will either get very reduced superconductivity, or in some cases no superconductivity at all. Okay, so that's the idea. This is the idea of a superconducting spin valve, very much similar in some ways to a metallic spin valve, but the physics is completely different. Okay, so here is my work. So this is the work done during my postdoc. And I'll show you that it's essentially the extension of this work that leads me to the TMR device. So what I do is I use a different ferromagnetic insulator, gadolinium nitride, 3 nanometer and 5 nanometer. This is the 5 nanometer switching. This is the 3 nanometer switching. So I can actually generate parallel and anti-parallel states, parallel anti-parallel states over here. And this niobium, when this is made very thin, so in this particular case it's 10 nanometer, what you see is that when you have the antiparallel state between the ferromagnets, you actually generate a superconducting response in the resistivity of this device. Okay, now another important thing, and this was again a prediction of Dijon's. So I cooled down another device. This is a 8 nanometer niobium device, and I measure this particular magnetoresistance at different temperatures. What you see is that the first switching is always constant. The second switching, you see, as I go lower and lower in temperature, the second switching increases in field. What that means is that once the superconducting state is initiated, like it is initiated at the antiparallel state of the ferromagnets, okay? Once the superconductor state is initiated, it does not want to destroy that state. The system wants to keep that superconducting state intact, okay? And this is as per the prediction of Dijon's. So this is actually happening because the superconductor, the Cooper pairs, they are all correlated in this very thin superconductor. They are carrying the information of both the ferromagnets, the exchange field of both the ferromagnets. So it's essentially like a situation where the two ferromagnets are talking to each other, okay? So it's a superconductor Cooper pair mediated net antiferromagnetic exchange coupling, very much like RKKY, but in the superconducting case, okay? And this was published about 10 years back. Yeah, so my work in IIT Bombay, a part of my work, actually builds up on this. So we make similar kind of devices, again gadolinium nitride. Sorry. Sorry. Yeah. So, sorry for that interruption. So again, gadolinium nitride, and we have niobium over here. So what we realize is that, see, if this is the magnetoresistance response of the system, then you can initiate the superconducting state and you can switch off the magnetic field. So when you initiate the superconducting state at the antiparallel field and you switch off the field, the superconducting state should stay, okay? I should be able to hold the superconducting state at zero magnetic field. However, when I reverse that same ferromagnet, when I come to this positive field and switch off, what should happen is that I should get a non-superconducting state at zero field, okay? So, you see, this is a very nice bistable switching device, okay? At zero magnetic field, I can change fields a little bit, and I can, toggle between these small fields and come to zero field, and I can measure very nice, completely superconducting state or a completely resistive state. And we have done many thousands of cycles. I'm showing you just a snapshot over here. The interesting thing really over here is that, you see, when I'm doing this cycling, like I'm basically switching between this field and this field, okay? So I'm going around in the minor loop of the hard ferromagnet. I'm doing the full loop of the soft ferromagnet. So this is the soft ferromagnet. I'm doing the full loop of the soft ferromagnet, but I'm doing minor loops of this hard ferromagnet, which is switching over here. So when you do several minor loops of a ferromagnet, what should happen is that there should be domain nucleation, okay? And the magnetization should change, and it should be not so easy to hold on to these perfect superconducting and resistive states. But because of that superconducting exchange coupling, what happens is that the actual magnetization states holds. Okay, so you see, like we have done like a lot of these, like this is magnetization as a function of time, as a function of these small magnetic field sweeps. You see the magnetization actually holds. So there is no domain formation in the system because of the superconducting exchange coupling. Okay, so this was published last year. You can do more cool things with it. So you can replace niobium with vanadium as a superconductor, and then you can do some calculations that can show you that, as I told you right in the beginning, you can actually engineer a device where there's only in the antiparallel state you will get superconductivity, and in the parallel state you will get no superconductivity at all. This is a special case. It's called absolute switching. Okay, what that enables you is that even at 0 Kelvin, where quantum circuits operate, you can actually make this kind of switch, which can hold on to these bistable states. Okay, so this is again nice results with vanadium, and this was published last year. And now the TMR device actually builds on these ideas, but yeah, let me show you. So, okay, so you see the operable range of this device is 0.7 Kelvin to 0 Kelvin. So let me now show you the device concept of the TMR device. So you see, this is the niobium device, and this is the vanadium device. So if you look at this, you see it operates between, if you are measuring the resistivity of this device, it will have two different resistance states between 3.2 Kelvin and 2.6 Kelvin, because below it, everything is superconducting in both the parallel and the antiparallel states. In the vanadium device, you do not have any superconductivity in the parallel state, but your starting temperature is only 0.7 Kelvin. Okay? Now, what if I wanted a device that, that should show this switching characteristics, let's say starting at 5 Kelvin and all the way down to 0 Kelvin. Okay? Do I have it through any of these? No, I don't have it. Okay? But if you realize one thing, you see, essentially what is happening in the systems is that you have two different TCs of the system. One is a high TC and one a low TC. So if you have two different TCs of the system, you should have a zero temperature gap, which should scale as per the TC. So you should have a high gap and a low gap that can be engineered in the same system. Okay. Now, the device concept is this, that, so this is the cartoon. So this is one TC, this is the another TC. If you measure at any temperature here, over here, there is no difference between the parallel and antiparallel state. The difference only comes in this region. However, if you were to measure the gap of this device, okay, you see at every temperature, you should be able to toggle between this red and yellow curves, okay, because the gap is higher in one and the gap is lower in another one. So that's the realization, and from the realization comes the device concept. The concept is that you make this tri-layer spin valve exactly the same way as before, and I want to do tunneling spectroscopy of this bottom superconductor, the thin superconducting layer. For that, what I do is that I grow a metal insulator superconductor on top, and I call that the tunneling spectroscopy counter electrode. Okay? Using this superconductor, I will actually do tunneling spectroscopy of this bottom superconductor. Okay. If I do that, what should happen is that the density of state spectrum, like with switching in field, should shift from a high gap to a low gap. So this is the gap of the upper superconductor. This is the gap of the lower superconductor. I should be able to toggle between these two. That should give me an IV response like this. And if I get an IV response like this, so this is the high gap, this is the low gap. So if I stand at a current, like some read current over here, you see I should be able to toggle between these two voltage states. And that should give me my bistable tunneling magnetoresistance memory. Okay? So what is the device that I make? So it's again the same spin valve layer at the bottom, and this is the actual materials. So the spin valve, then aluminum oxide, niobium. Very complicated fabrication. I'll explain it if there are questions there. I'll not go into the details of that. And this is the image of an actual device. So this is the top view. So you're looking from the top of this niobium layer. Now this niobium layer is the top contact layer. It's a superconducting contact. And that's your device there. Okay, it's a 5 micrometer by 5 micrometer device. Okay. Okay. So first benchmarking. So I'll just do current in plane measurement of this spin valve type 3 layers. to get the usual characteristic, to check whether I get the usual characteristics. We do get those usual characteristics. And this particular device has two well-defined TCs, one at 4.2 Kelvin and one at 3.8 Kelvin. Okay. Now comes the real important part. Are we able to tune the gaps of this superconductor? Ideally we should, and are we able to measure that? Okay, so I'll show you that the gap should actually behave in this way. Okay, it's expected to behave this way, and these are the results. Okay, what I do here is that I come to a temperature, I apply either the parallel field or saturate it and go to the antiparallel state, create the antiparallel state, and then I measure the di by dV, or it's a lock-in based measurement. I do at like one temperature, then I move on to the next temperature and again generate that state. And what you see here is that, you see, like this is the parallel state. I should have a lower TC and a lower gap. My gap is going like this and exactly matching like the TC parallel point, which is actually this. So 3.8 kelvins, this is around about 3.8 Kelvin. And the antiparallel state gap, which is higher than this gap. And you see, it comes down and reaches 0 at around about 4.2 Kelvin. Okay, so very beautiful measurement. I like this measurement very much. Okay, so we actually get this functionality. So if we get this, I should be able to get the memory device as well, right? I should be able to do the memory measurement where I should be able to toggle between these two gaps, and I can generate a tunneling magnetoresistance resistance type of memory. So let me show you that we can do that. Okay, so this is the cartoon representation. So sorry, this is the cartoon representation, and this is the actual measurements. So here are the IVs, and here are the di by dVs. Okay, that's the differential conductance, which is actually the density of state. So at a temperature which is between the two, at a temperature which is between the two TCs, that is 4K over here. So remember, one was 3.8K and one was 4.2K. So at 4K, what should happen is that you see the yellow curve here, like this is at a parallel field. There is no sign of any kink in this spectrum. But as I go into the antiparallel field, so minus HC of F1, the first layer switching, you see there is a kink that develops over here. So that's the gap of the superconductor, the bottom superconductor that is developing over here. And similar happens at much lower temperatures. The signal is much more sharp, and you see this bulge that we predicted. You actually see this bulge in this IV over here. Okay, so now we put a read current. Now the experiment is very simple. We put a read current, and we go through the field cycles, and you see there's this nice bistable response. So this is practically my last slide. Nice bistable response. And as I told you, like we can not only get it here, we should also be able to get it at the much lower temperatures. So at 0.25 K, thermal effects are gone, and I have this very nice bistable switching in this device. Okay, so that brings me to my conclusions. So spin-dependent phenomena can be engineered in superconductors. Superconducting spin valves, they are in some way similar to metallic spin valves. They can be used to make dissipation-less memory devices, and TMR response can be generated. And there should be no reason why this device is not scalable. Okay, so this should be scalable down to the probably 100 nanometers level. So this should be a industry adaptable device. Okay, these are results that are under review. You can, if you want, you can read this paper in archive. And this is my research group. This is actually Sonam's work. Sonam is sitting there. She has submitted her thesis. And Abhijit, Subhashri, Pawan, and Animesh are all there in this conference. They have their posters there. I hope you will visit their posters. And there was a time when I used to get funding. Now I don't get it. So that was from DST and National Supercomputing Mission. That was ages back. Anyway, so I should acknowledge them. Thank you very much for patient hearing. Yeah.
Thanks, Abhijit, for sharing these beautiful results.
Thanks.
Time for questions.
So what is the smallest magnetic field it can detect?
Yeah, so these are what it can detect. I think that will depend on currently it is a few milliteslas currently, but I think you can engineer that, and like with different materials, with different kinds of heterostructures, yeah. And it can go much lower. Mhm.
Hi, a very nice talk.
Oh, hi.
So, I just wanted to know one thing. Is there any means critical thickness of this vanadium and niobium
Yeah.
beyond which you will not get superconductivity?
Yeah. So there is this dirty limit coherence length that becomes the limit of this. So typically, like the dirty limit coherence length of these materials, like depends on the thickness that you grow. So typically for a 10 nanometer niobium, it would be around 13, 14 nanometers at most. So, and as you make it thicker, what will happen is that this exchange coupling will also reduce. Okay, so I would say you can get this to about 12, 13 nanometers in either of these films.
And also just one more point that if you are having this okay.
Sorry.
Maybe
I will after
we'll postpone it for
Yeah.
the discussion
Yeah.
session. Anybody else? Quick question.
Yeah. Hi, Dhamla.
Yeah. Thanks for a nice talk. Just in the tunneling device data, right? I have. Okay, say this one also is fine.
Yeah.
I have two small questions.
Here.
Don't you think the IV curve is too broad? And second
Yes.
is the critical currents that you're quoting, right? It's in milliampere, isn't it too large?
So these are
It's,
So
like how do you get rid of Joule heating?
right. So firstly, it is broad. That's true. But like it's niobium. It's a typical problem in niobium. It has spin orbit scattering, Dyne's parameter, and all these things. And not only is it niobium, it is very thin niobium. Okay, so that's why the IV curves are broad. So you're right in that. And so these currents, you see, the currents will depend on the size of the device. So because this is a 5 micrometer by 5 micrometer device, you have currents that are of this magnitude. But if you scale them to the nanometer level, this will go down to, I think, some nanoampere levels. That's entirely manageable. Yeah.
Okay, so let's thank Abradeep again
Thanks.
for the nice talk.